Hi there students, this is Dr. John, your physics and math professor, and today we're coming to you with the physics of buckets, which is where we would have something which would be tied in series like this. You're going to have a similar kind of problem where you may have a train pulling a number of different railroad cars, and you're asked to find the tension between each of the railroad cars. Well, we're doing sort of a very simple model of that here today. We have a rope here, rope A, pulling this paint can up or down or whatever direction we're moving, and it's attached directly here to the second paint can, each of them having the same mass of 2.8 kilograms. We're asked to find the tension in this rope and the tension in this rope. Here I've just drawn a smaller representation here because I'd like to mark this up here a little bit as we progress in this problem. So we have two different aspects of this problem that we want to do. One is if this whole thing is moving downward at a constant velocity, 2.4 meters per second. No acceleration, just constant velocity moving downward. The other one is what if it's accelerating upward at 2.4 meters per second squared? Notice the units. This is squared. That's just meters per second. These might have slightly different answers. Let's see how we might approach them. To do this, we're going to need Newton's three laws. Now, I'm not saying you need to memorize it totally and exactly the words that they may have it in the book, but you need to have a general concept of what the three laws are. The first law is just simply the sort of the law of inertia. That is, if something's moving at a constant velocity and there's no forces outside of it pushing it or pulling it or trying to make it go faster or slower, there's no external forces, it's going to continue to go at that same velocity. Whether it's standing still or whether it's moving at a constant speed, that's not going to change with no external forces. The second one is this: if there is an external force, especially a net force, which means the total force in the system, that's going to be, the force is going to be equal to the mass times the acceleration. So the first one says it's not going to accelerate without an external force. The second one says if it does have an external force, this is how it's going to accelerate: the mass of the object times the acceleration. Then the third one is a little bit unusual. It says that for every force, there's an equal and opposite force. So if I lean on the wall here, the wall is going to lean back on me. Unless the wall crumbles down, then there's a net force in that direction. I'm standing on the floor is pushing up at me with the same force that I'm pushing down on the floor. So those are the Newton's three laws. We're going to use those in all of these different problems with ropes and tensions and buckets and cars and all those kinds of things. So let's take a look at this problem here. First of all, what if it's moving downward at a constant velocity? Now, if something's moving at a constant velocity, Newton's three laws, there are no net forces. So let's just take a look at this here. I'm just going to put dashed lines around this entire thing here. Let's say we want to find the tension in rope A if it's moving at a constant velocity. If it's moving at a constant velocity, you can do it, the problem, just the same way as you would if it's just sitting still. It's not moving at all, which would mean this tension here is going to have to be equal to the weight that these two buckets have downward, which would mean tension A is going to have to be equal to the combined weight here, which would be M1 plus M2, which is 2 times M times G. Or if we want to be specific, let's write down 2. M is 2.8 and gravity is 9.8. This here is about 5 times this. That's going to be about 50. We'll do the exact numbers in just a second. I just want to do both of these right away, and then we'll do the calculation. So tension in D, that's in this chord here, we wouldn't draw a dotted line around the entire thing. We would just draw a dotted line around this thing right here. And we would say, what are the external forces acting on this? Well, for one, it's tension B acting upward, and the other is this mass acting downward, which would be big M times G. And if we want to be specific, it's 2.8 times 9.8. Now, if you notice here, this here is exactly the same as this, except it has a 2 in front of it, which means the tension in rope A will be twice that of the tension in rope B, which sort of seems reasonable. Let's just do these calculations. I'm going to plug them in, and we'll see what we get. Okay, I've done the calculations here. I've just multiplied it out straight on my calculator. I've got 54.88. Here I've got 27.44. Notice here we have two significant figures. Here we have two significant figures. So we'll want to round these off to two significant figures. This would have to go up because this is bigger than 5. This is 5 or up. So this is going to have to be equal to 55. And this one would go down. So it's going to be 27. It doesn't look quite like it's half, because if you double this, you're going to get 54, but it's because of our rounding time. So for the first one here, let me just write that in here. For A, always do your rounding to the significant figures right at the end when you've done all your calculations and you're trying to get your answers. You could put a decimal in there if you wanted to. It wouldn't make any difference. It's two significant figures. I'm going to erase a couple of these things here and start over here with the second part of this where we have an acceleration upward. So here I've erased a couple of things over here and I've redrawn this box. What we want to do is we want to look at this because we want to look at the tension in A. Remember, A here, the rope here sort of goes outside of the box. What else goes outside of the box? Well, obviously there's going to be a force of gravity going downward like this, force of gravity. So the force of gravity will be coming below the box and the tension A will be coming above the box. This thing inside the box here matters not. You could just as well attach these two pails, hook them together if you wanted to. Let's just do this one at a time here. So here notice the question tells us that we're accelerating upward. So what we have from Newton's law right over here is that the net force, the unbalanced forces, the forces when you take all the forces and subtract them. So the mass times acceleration, the mass times the acceleration is going to be equal to this force up here, because that's the tension in A. That's the force pulling it upward. Remember, we're saying we're accelerating upward, so I'm going to put this one first because it's actually going to be bigger. This one's going to be bigger than this one down here. And then we have to subtract the forces that are trying to keep it going this way, which would be the force of gravity, which just like before is going to be equal to 2 times m times g. So on the right side here, this would be the sum of all forces, these two things over here, or the force net. If you wanted to, however, people may note them a little bit differently, just writing those in there so that you can see different ways people might write that. So this would be the net force, or the unbalanced force. Unbalanced does not mean it's crazy or something like that. It just simply means that there's more force going up than going down. The tension up is more than this. So this is going to be equal to the mass times acceleration. Of course, when we do the mass times acceleration, we have to be careful. Which mass is accelerated? Well, it's going to be 2m times acceleration. So this, we have to be very careful here. This m here is like this. It's 2m. So let's write these things in here. So this is going to be equal to tension A minus 2m times g. We want to solve for tension A. So let's take this to the other side. I'm actually going to move this over here, tension A. So just don't be confused. I'm sort of flipping sides here. I'm going to move this to this side. So that's going to be equal to 2 mass g plus 2 mass acceleration. So notice what I did here is I took this to this side. So these are both positive, just like here. TA is on this side. I just flipped everything so I could have the tension on the left side because we like to write the thing we're looking for on the left side. Now let's take out some common things here. This is equal to 2m g plus acceleration. That's going to be the tension A. This is a common way you're going to see pulleys and ropes and things like that. You're going to see some sort of G plus acceleration, G minus acceleration, especially if you're doing it up and down like this. So don't be surprised if you have something like this. We're going to erase a few things here so I can write the numbers in there. I'll just erase all of this. I don't think we need that right now. So you have just rewritten this. I've taken this equation, written up here, and then I've written in the specifics. M is 2.8, just like both of them are the same. 9.8 is gravity, and 2.4 is the acceleration. Now, because we've already built in the idea of what direction things are, the direction tension is and all that, these are just going to be positive numbers. We don't have to worry about it being positive or negative. So if we multiply this out, this is going to be about 5. This is going to be about 10. It's going to be a little bigger than 50, say 60 or 70. So I'm going to say about 70. Let me look it up and see what number I get. So here the answer I got was 68.32, pretty close to my guess. I always like to guess things because that way if you make a stupid mistake with your calculator, you're going to have one more way to catch your mistake. So 68.32, let me write this in here. So the answer is to be, everything's getting pretty crowded here. TA is equal to, remember we're going to drop this to two significant figures, just like we have here and we have here. So the 32 is less than 0.5, so we're going to just make this 68. 68. Of course, this is newtons, newtons, and newtons here. So let's check TB here. Just erase a couple of things. We'll do it again. So for the tension in rope B, what we would do is we would isolate just this pail here. And then we look at this pail and we say, what forces are acting on this? Well, we know that the acceleration is upward. So it's going to be mass times acceleration. This is going to be positive in this direction. So we're going to take this as positive. And all we're concerned about is the tension here, We don't care about this because this is the thing that's going outside the box. So it's going to be equal to TB minus the mass times the acceleration of this, which would be mg. Now in this case, this m is just one of the m's, so we don't have to put the two m's in there. Remember, we want to solve for TB like before, so let's take this to this side. TB is equal to mg plus ma. Remember, I took this over here. I'm getting mg plus ma equals TB. Then I just switch the whole side. The equal side is like a seesaw. You can go to either side of the seesaw and it's still equal. Now we have, of course, we can take an m out of this. We get g plus a. Now, if you remember from before, this is identical to this one, tension up here, only here we had a 2 in front of here. Let's write the specific numbers in there. 2.8. This is going to be about 10. This is going to be about 3. So it's going to be about 35. So here I have the answer from my calculator, 34.16. I know that seems extremely close, but actually I did guess. I was guessing. And since we have two significant figures, we'll just drop to 0.16 because it's less than 0.5, and we're going to be left with 34. So in this case, it's going to be TB is equal to 34 newtons. So just take a look at this here a little bit. When we're not accelerating, we're just moving the tension in the first rope here is 55, second rope is 27, about half, and this one here is 68, this one's 34. Notice the tension is higher in both cases when we're accelerating upward. As it should be a little higher, but it's not ridiculously higher. This one's 55, this one's 68. If your answers are ridiculously higher, you may have done some math mistake or some setup mistake. I hope that helped. If it did, like and subscribe and check out some other videos. I will see you there. Bye-bye.